Hello students, in this lecture, I want to show you how to calculate d-spacing from XRD data by using the Origin software. Here is the Bragg's law. According to the Bragg's law, n lambda equals 2d sine of theta, where n represents the order of reflection, lambda is the wavelength of the X-ray used, and d is representing the d-spacing, also called interplanar distance, and theta is the diffracted angle. Here is the X-ray machine where there is a X-ray tube, X-ray hits on the sample from the X-ray tube and then diffracted, which further detected by the detector. Sample could be either in powder form or somehow in pellets or coating on substrate. Here you can see by the blue dots, the representing some planes in the sample. So blue dots representing different planes, and the distance between the two planes is d, and that d is actually the d spacing, and this is what we are going to find today. Okay, so let's start with the basics. What is crystal? Crystal is nothing but consists of lattice plus basis. Lattice is a periodic arrangement of imaginary points, and basis is nothing but number of atoms on the imaginary points of the lattice. So periodic arrangement of unit cells into a lattice is actually representing a crystal. Now, what is unit cell? A unit cell actually contains a single atom or number of atoms, and it is a smallest building block of the crystal. So crystal actually consists of planes of atoms that are spaced with some distance, d. Now let me show you some atomic planes and d spacing in a simple cube. Suppose here is a simple cube where A, B, C are the lattice parameters having the intercepts on the crystallographic axes. The reciprocal of these intercepts, which plane makes with crystallographic axes, are actually nothing but Miller indices. And these Miller indices are actually showing the orientation of planes. So symbolically, these are representing by H, K, L. So here we have one of the plane that is 100, and the distance between the two planes that is representing by t, having some numbers you can see here 100. Those numbers are nothing but h, actually representing the hkn, means representing the Miller indices. Here is another plane that is 111, and here you can see one of the plane that is of 110, and here in this figure you can see one of the plane that is 012. Here is XRD data representing different planes in a cubic structure. Here, Bragg's law is fulfilled for 100 planes at around 20.6 degree of 2 theta, that producing a diffraction peak. Here you can see 100 planes which are supposed to be diffract at 29 point something of 2 theta, but you see they are not properly aligned to produce a diffracted peak. If they are properly aligned like this one, then of course diffraction peak would be produced. So because they are not properly aligned to produce a diffracted peak, and we observed only the background of planes. As 200 planes are parallel to 100 planes, so they are diffracted as well, and they are diffracted at 41.2 degree of 2 theta. So please note that the dotted lines actually representing the diffraction vector, means the vector that bisects the angle between the incident and diffracted beam, and the red arrow representing the plane normal, the direction perpendicular to a plane of atoms. So both should be parallel for getting the diffraction peak. Let's start. Click on the analysis and then peaks and baseline, and further select the multiple peak hit, and then open dialog. Once you do that, you will get this window. So simply click on OK. Okay, so now this window will open. So according to this window, now you will click 2 times on each peak. Okay, so by doing this, I selected the first peak, and then I'll select the second peak and the third peak and the fourth peak. Okay, once we selected all of the peaks, we will click on the open fit option. So okay, so this window will open. Here simply we will click on this window, on this option where all of the calculations will be done. So simply click on this and then click on and after that click on done. Okay, so now you can see peaks number were appeared along with the peaks now. So here simply we will select this option and then click on OK. So here you can see all of the selected peaks along with all of the data which were calculated after doing all of the previous steps. So now, okay, so now I'll simply go back and click on the workbook. Click here. Yeah, this file will be open where all of the data is given. So here let's check the summary. Yeah, this one where you can see we have all of the angles related to each and every peaks because we have selected the 4 peaks. So you can see the first peak is at 18, the second 36, and the third one is 44, and the fourth one is at 64 point something. So simply we will copy all of these values and then okay, so here is an Excel file that contains all of the peak position values, and these position values can be further used to find the theta, and that is very simple. We will just divide the two theta values by 2, and then we will get the theta values. So once we have theta values, now by calculating the d spacing, here is the formula, and this formula I have written, and exactly the formula which I have shown on the first slide of this lecture. So by using this formula, we can calculate the d spacing for each and every peak. So here is the d spacing values corresponding to each and every peak. So that's all for the today's lecture.